Descriptive analysis is a broad and relatively unbounded subcategory of AI. We will try to group it under four types. The first of which is statistical analysis of data. This could be done with one particular data field, like computing average age of a population, or multiple fields, like average age of a population by country. Another type of descriptive analysis involves making trends. Example, how does the average temperature vary across the year? The third type of analysis important for business operations is process reporting. Example, real-time stage tracking of your pizza delivery order. Finally, another valuable type of reports involve exception reporting, which highlight relatively infrequent but important events. As an example, which road should be avoided as you're driving to not get caught in traffic jams or delays due to accident. Let's learn more about these four types of descriptive analysis with an example of a car manufacturing operations. There are four steps in the car manufacturing process at a high level. The first is called press shop, where large amounts of metallic sheets are pressed into various automobile panels. This is a bulky part of the overall process and is thereby driven mainly by large machines. The second shop is called the body shop, where individual car panels are forged and welded to make the car outer body. This is done by a combination of machines and humans using some ergonomic tools. The car body is then passed on to the paint shop, where it is painted by some machines with finishing touches by highly specialized staff. Finally, the painted car body gets into a general assembly shop where all the parts ranging from the engine to the car seat are fitted together to build the car. It is then sent for testing. The proportion of human work as opposed to machines increases gradually as we go down from the press shop to the general assembly shop. Imagine if you were the operations manager of an automobile manufacturing company. You had granular data on which parts took how many days to finish processing by different shops for a full month, let's say Feb of 2020. In body shop, many parts from the press shop are welded together, so we can assign a body ID at this stage which can be followed through the paint and general assembly shop. In the general assembly shop, the processes depend on the delivery of parts like tires from external suppliers. Your general assembly shop always targets to have at least two full sets of available supplies at any given time. If you maintain a lower level than 2, there is a risk that the general assembly work gets delayed, as painted cars have to wait for the external supplies to get delivered. On the other hand, if there are more than 2 sets of available external supplies, it creates logistical challenges of storing them. Many manufacturing plants thereby work on the principle of just-in-time delivery of the external parts. Let's start with the statistical analysis part of descriptive analysis. First, you could do some frequency charts. For example, what are the different parts produced in the press shop for the month? Example, it looks like parts required for 56 cars has been produced for the month. Then you can look at distributions for number of parts produced by days taken for the different shops. Since press shop is largely machine driven and there are a variety of parts produced here, it's no surprise that we see a normal distribution of number of parts produced by days taken. A normal distribution is symmetric, with most of the observations clustering around the central peak and occurrences taper equally from the mean in both directions. Most naturally occurring randomized events follow normal distributions generally, like body height of the population. Please note the press shop output distribution is shown on secondary axis here because of a high number of outputs produced. We can see that the body shop and the paint shop produces output with a uniform distribution. The exception in body shop are some outputs that take more time due to defects in the welding process. The general assembly shop is dependent on external supplies like seats and wheel. An irregular batch delivery of these supplies may create a noisy distribution of number of days spent for the painted car in the general assembly shop. We can also create cumulative distribution that sums all the previous occurrences to a particular point. Example, about 35 car bodies out of 56 spent 18 or less days in the body shop. The second type of statistical analysis is measuring central tendencies. Mean is the total of numbers divided by how many numbers there are. It is the most commonly used measure of central tendency. Median is the number which is at the middle of the distribution. Mode is the number that appears most frequently. For a normal or uniform distribution, mean, median, and mode are identical. For body shop, since it has a higher concentration at higher number of days, the median is higher than the mean. The third type of statistical analysis is measuring spread tendency. Standard deviation is a commonly used metric for this. As body shop distribution spreads most, it has the highest standard deviation. The fourth type of statistical analysis is measuring divergence from normality. Skewness is the most commonly used metric. If the distribution is skewed relatively more to the left, the skewness value is negative. For the right skewed distribution, the skewness value turns positive. We can also look at confidence intervals of data fields. Example, outputs are produced in the press shop in 10 plus and minus 7 days for 90% of the time. For body shop, it is 2 to 25 days. Finally, within statistical analysis, we can look at scatter plots and correlations between two data items. Example, the number of sets of supplied parts available on the date of entry of a painted car in the general assembly shop versus day to finish processing in the same shop. If there were no parts available, it would take longer time to finish processing in the general assembly shop as there may be a wait period for the parts. Correlation is a calculated metric that varies between +1 and -1 and measures the tendency of two quantities to move together, whether in the same direction or in the opposite direction. Since lower number of supplied parts causes delays resulting in a higher number of processing day in the general assembly shop, the correlation between these quantities is negative. Correlation, though, does not automatically imply causality, and we shall look into this in more details in future sessions. The second broad category of descriptive analysis is trend analysis. One variety of that is vintage analysis, where we look at equivalent batches by time since an event. Example, average number of outputs by days since day of input into the press shop shown for the last 3 years. The distribution has become more normal with smaller spread as the press shop may have deployed more heavy machinery recently. We can also look at trends by calendar months or years. Example, there is some production decline due to seasonality in December. The third category of descriptive analysis is process reporting. Example, we can look at the average number of FTE available each day for February and March 2020 for various shops. As the reliance on expert human work increases in successive shop stages, the availability of FTE in later stage shops in March 20 has declined more, probably because of social distancing requirements due to COVID-19. We can look at intensity reports, which in this case shows a decline at an even higher rate in March 20 compared to availability of FTE. This could be because there is more time spent on sanitizing machine parts and wearing personal protective equipments due to COVID-19. Effectiveness reports can show number of output units produced per unit time period. Finally, efficiency reports can show number of output units per input unit, in this case the productive time. Since productive time already corrects for lower number of FTE and extra time taken for sanitization and protection, the efficiency drop here in March is not explained and should be further investigated. Finally, some exception reporting can be done to highlight things like policy breaches. In this example, it's useful to know for how many times when the painted car entered the general assembly shop there were no supplier parts available, as that causes delays. As discussed before, it is also not valuable to have a high number of supplier parts available, as that causes storage challenges. Let's bring all the types of descriptive analysis together to give you a final framework for your own use. Finally, couple of occasions when descriptive analysis could be misleading and should not be used. First, if you want to make granular decisions on your operating processes, like should you be getting the supplier parts ordered earlier to solve for the wait period in the general assembly shop. This is a separate piece of analysis that needs to look into trade-off between delay and storage costs. Secondly, for making inferences on larger population sets, descriptive analyses are challenged by sample bias and attribution bias. Example, it may be inaccurate to project similar level of productivity loss due to COVID-19 across various factories located in different geographies.